Welcome to our data mining lesson video in which we are going to review linear regression. Linear regression is a form of regression in which we assume the output variable is a linear function of the input variables. In this plot we have shown on the screen our output variable is sales, and we're assuming it's a linear function of our input variable TV advertising. So sales, that's a function of the amount of advertising that's expended on TV by a company at some time. And so each red dot in this plot represents a different observation of a company with their television expenditure on sales and the amount of sales. And we're estimating this as a linear relationship, which is shown in the blue line. And then the vertical gray or black lines show us the amount of error for each estimate, which is the difference between the actual value with the red dot and the predicted value on the blue line. We're more concerned in this course about cases where you have multiple input variables. So in this case, we're showing sales and a approximated linear relationship between the sales and the expenditures in TV and radio. The formula we use to describe this linear relationship is shown on the screen here. And so Y is our output variable. Beta naught is the estimated amount of output variable if all the input variables, meaning all our x's, were 0. Then we have our linear combination of our input variables. And then we have this epsilon, which is the deviation between the linear model and the actual output variables, which we think of as error. It incorporates everything that occurs that is not covered by our linear regression model. When we build our model, we estimate the values for the betas off of the data. The estimated values for the betas are called beta hat. So anytime we see a hat statistics, it means this is an estimated value for something. And so we have our linear relationship with our beta hats, and if we find a new observation, which is this x1, x2 out to xp, we could put it in this formula, and that will get our estimated value for y. We estimate those beta hats using this formula for residual squared error below. And to understand this formula, for each of our inputs, we could use those beta hats and get a y hat. And that y hat is right here in the formula. This difference between the y hat and yi is the error in the estimate. So we square those errors and sum them up. And that allows us to find these beta hats, which are estimates for all the coefficients. Two things that come up that are very important in linear regression that we're going to talk about today is how good of an estimate is each of our beta hats for the actual value of beta. So how well are we doing approximating some real linear regression model? And correspondingly with each of those, how important are they? How sure are we that each of those betas is not 0, right? It could be that the beta might be 0 and we don't really need that variable. That variable is not significant. The second thing we're going to talk about in our presentation today is how large is this epsilon, meaning how good is our fit from our linear regression? Is our linear regression doing a good job fitting the relationship between inputs and outputs, or is it doing a poor job? So a couple of factors that we need to consider in estimating the importance and goodness of the betas, as well as the goodness of the fit. First, a little bit of terminology. The regression coefficient, this is something we've talked about in the previous slide. It's just the estimated amount of change in y that will occur for a given 1 unit change in xi. So that's the interpretation of those regression coefficients we saw in the previous slide. There's something called the standard error for regression coefficient, shown by the formula on the right-hand side in the slide here. And this measures the amount of uncertainty in the estimate of beta I. So it acts like a standard deviation in the estimate of what the beta I is. It tells us how sure we can be that our beta I hat is close to the actual value of beta I. Next statistic that we're going to look at is the t statistic. And the t statistic is the number of standard deviations that our beta I hat is above 0. It's given by this formula. It's the difference between beta I hat and 0, and then divided by the standard error for beta I hat, which plays the role of a standard deviation. So if the t statistic is large, say 5, that means that our beta I hat is like 5 standard deviations above 0, so it's not likely to occur, or not likely that we would see something that high if the beta I were actually 0. The t-statistic and the p-value give us some measurement for the significance of a variable or for a coefficient for a variable. Significance meaning that how sure are we that that coefficient isn't zero, or that parameter input variable is not actually playing a role in our linear regression. P-value is just another way to measure the t-statistic. It's a probability getting a t-statistic of whatever we achieved in absolute value or larger if beta I were equal to 0. So small p-value indicates that the variable is more significant or is playing a larger, more important role in our linear regression. So some metrics that allow us to evaluate the fit of our linear regression. There's residual sum of squares. That's what we talked about early on. That's what's minimized when we're choosing our beta I hats. The smaller that is, the better fit we have. There's a residual squared error. So this estimates the standard deviation in the error epsilon, right? Or the average amount of error that we're getting between our predicted value and our actual value. Formulas given on the right-hand side of the screen here. The third method for measuring the goodness of fit of our linear regression model is called R-squared, and it's the proportion of variance in Y that can be explained by our input variables X. And so we can look at the formula that's on the right-hand side here to help us understand this. So here's TSS, which stands for total sum of squares. So that's the total variance that's in Y. And then RSS, which is the residual sum of squares, that's the variance that's not explained by Y, or the error variance. And we subtract these two in this term in the top, we get the amount of variance in Y that is explained by our linear regression model on X. When we look at the bottom of this fraction, we have total sum of squares, which is the total variance in Y. In review, we've talked about linear regression in this video. We've talked about some important ways to measure our linear regression, first measuring our estimates of our betas, then measuring the input variable significance, and then measuring the regression fit. Thank you very much.